The topic of my talk falls in the area of soft condensed matter physics, criticality, dynamical criticality in cell differentiation. And we know that living matter is a very good example of soft matter. We know that tissues make up organs in our body and cells make up tissues, and they are soft condensed matter at different spatial scales. So what is cell differentiation? Actually, this is stuck probably at the, please come. এটা না হ্যাঁ এইটাই তো এটা বোধহয় আটকে গেছে এটা না full scale it will be reduce in size. Normally what I do is I operate the arrows. Right. So in an embryo all cells are identical. And what is cell differentiation? Stem, you have heard of stem cells. Stem or progenitor cells, they diversify into different cell types and the organism starts developing. So different cell types means liver cells, kidney cells, etc. And stem cells exist in both embryo and adult tissues. Remember that stem cells are undifferentiated cells, and cells, all cells have identical sets of genes. So, and different subsets of genes are active in different cell types. For example, we know that there is a protein called hemoglobin in red blood cells. So hemoglobin gene is active in red blood cell. The gene exists in the kidney cell, but it is not active there. And gene activity results in protein synthesis. So this is what is known as the full screen. Probably people will not be able to see at the back. Will you do it and try, or maybe I'll just operate?
You can come back immediately.
Okay. It is probably too small, no, from the back? Make it full screen.
Remove.
Remove. Hey, it is stuck. Pratap. আমি এটাই না আমি এটা দিয়ে অপারেট করতে চাই হচ্ছে না হ্যাঁ ঠিক আছে হ্যাঁ সো ওকে না ইটস ওকে প্লিজ হ্যাঁ losing precious time.
Okay,
right. So see, this is the mammalian sulfate tree. So this is the mammalian sulfate tree. So at the root you have the stem cell state. And see, this tree consists of binary branches. At each point the cell has to decide between two lineages. Should I differentiate into this lineage or that lineage? And these lineages are transient in nature. So ultimately what happens is the following. The cell ends up at the terminal branches or leaves. And these are the stable cell types. Liver, kidney, brain, etc. So why is research on stem cells so important? It is one of the most active areas of research in biology. Why? Because suppose you have heard of stem cell therapy. Suppose somebody's kidney cells are damaged, kidney is not functioning. So in stem cell therapy, the idea is that inject stem cells into the kidney, and the expectation is that in the appropriate environment, these undifferentiated stem cells will differentiate into kidney cells, the damaged cells will be replaced, and the kidney can function in the appropriate manner. This is the idea. But there is a vast gap between idea and execution. So all over the world, people are doing research on stem cells. And hundreds and thousands of experiments have been carried out on cell differentiation. And people have identified a common motif in many of the gene regulatory networks. So there are two genes, X1 and X2. X1 gene synthesizes protein X1, and X2 gene synthesizes protein X2. And these proteins can regulate further protein synthesis. The process of protein synthesis is called gene expression. So these proteins repress each other's synthesis. This symbol, this is a hammerhead symbol, this represents repression and this is activation. So here we have a double negative feedback loop, and it is equivalent to a positive feedback loop. What is a positive feedback loop? You connect the input with the output. And why positive feedback loop? That if you increase the concentration of one component, that will give rise to further increase in the concentration. So there are 3 positive feedback loops, one here, and the protein auto-activates its own synthesis. So there are 3 positive feedback loops, and the idea is something like this, that you have a progenitor state, and then it differentiates into 2 cell types, cell type 1, cell type 2, and they are distinguished by protein levels. In one cell type, X1 is much less greater than X2. Remember, X is the protein concentration, and in the other, X2 is much greater than X1. That is the idea. So now enters the physicist into the picture. So what is the physical principle underlying cell differentiation? Can we answer the question? So cell differentiation dynamics have both deterministic and stochastic components. So I'll quickly give you the deterministic description. See, the proteins are playing the main role. And so define the state of a cell at time t. This is defined by protein concentrations X1 and X2 at time t. Remember, in the motif we had 2 genes synthesizing 2 proteins, and the concentrations are at X1 and X2. So you can define a state space which is 2-dimensional with axis represented by protein concentrations. The state at time t can be represented by a single point in state space, and time evolution of the system. Remember, the gene synthesizes protein at a specific rate, and proteins have half-lives. They are not stable products, so they can also decay. Birth and death both are possible for proteins, so there is a time evolution of the concentration of proteins. And so time evolution of state is represented by a trajectory in state space. And dynamics is governed by a pair of differential equations. There are 2 proteins, and they replace each other's synthesis. I am happy that Prof is listening. Prof, fantastic experiments are being carried out in this area. So this is a mathematical model of cell differentiation, and we proposed the model in 2015, and recent work 2017. Again, the toy cartoon is here, and X1, X2, remember, are the protein concentrations. The first term represents auto-activation, the second term mutual repression, and this is the degradation of the protein. This is like radioactive decay, and this is that these 2 proteins can form a dimer. So this is heterodimer formation. So you can use typical chemical kinetic schemes to write down the differential equations. And remember, the X1, X2 are variables, and A1, B1, S, K1, G, these are the parameters in the system. Where is positive sign? This is negative because this is degradation of protein. So in steady state, all rates of change are 0. Protein concentrations assume fixed values. So this defines what is known as the fixed point of the dynamics. So this is the endpoint of trajectory in state space. So we will deal with a phenomenon called biostability, coexistence of 2 stable steady states for the same parameter values. So Max Delbruck, long back, and Monod and Jacob, they were physicists originally, and they said that biostability forms the basis of cell differentiation. Because see, in cell differentiation, the cell has to go to 2 stable lineages. So 2 stable steady states are necessary. So biostability is needed. And the 2 stable steady states differentiated cell states with X1 greater than X2 and X2 greater than X1 respectively. This I already showed you. So in our model, we considered the symmetric situation that these parameters are equal, these are equal, these are equal, and then we solved the differential equations, found out the fixed points. Yes? A binary? It's mainly binary. No, binary, right. Which one? Leaf. Yes. The binary, that originally you have one state. After differentiation, there is a choice between 2 states. So how the choice is made, we have to answer that question. There are 2 possibilities. So cell differentiation from monostability, to use the language of dynamical systems theory, that only one stable steady state, undifferentiated cell state, we are going to bistability, two differentiated cell states. So we showed that, we solved the equation, put rates of change to be 0, solved the equation, and we found what is well known as supercritical pitchfork bifurcation. So these solid lines represent stable steady states. This is monostability, just one single stable steady state. This is known as the bifurcation point. This value, the value of A is equal to AC, it's like a critical point. So as soon as the parameter goes beyond AC, you have two stable steady states, a pair of new stable steady states appear in the system, and this original stable steady state becomes unstable. This dotted line represents that it is an unstable solution. So bifurcation involves change in the number and stability properties of steady states. See, at the bifurcation point, or before the bifurcation, one stable steady state, after that two stable steady states. Before the bifurcation point, this was stable. After the bifurcation point, this became unstable. So there is a change in the dynamical regime in the system. So this is reminiscent of critical phenomenon, phase transition. Transition from monostability to bistability occurs at critical parameter value A equal to AC. Reminiscent of phase transition. So in my talk, I will convince you that, that we have given evidence which has been corroborated by actual experiments that cell differentiation is a case of bifurcation, and whatever experimental evidence people have obtained, they are signatures of criticality. So I don't know how much I can cover, but I described to you the deterministic dynamics, but let's now go over to stochastic dynamics. Bistability is outcome of deterministic dynamics, so there is absence of randomness. In a population of cells, same protein level is obtained in each cell, because you are solving the same differential equation, same initial state, you expect the protein level, steady state protein level to be the same. In reality, biochemical events involved in gene expression are probabilistic in nature, giving rise to fluctuations, noise around mean protein levels. So this is the cartoon. So this is the mean level, the solid line, but in an actual experiment you will see lots of fluctuations around the mean level. So instead of, in the absence of noise, you have a single protein level, and due to stochastic nature of gene expression, you now get a distribution of protein levels, and the width, the variance gives you a measure of noise. And there is a beautiful article, the cellular hullabaloo. This came out in Nature. Actually, fantastic experiments are being carried out, single cell experiments for the measurement of noise, the factors on which noise depends and things like that. The inner life of a cell is noisy. So I'll show you a cartoon. Two genetically identical cells kept in the same environment can behave in dramatically different ways due to noise. This is the mother cell and these are the daughter cells. So one daughter might go dormant while the other stays active. So this is a cartoon for noise, and noise can be quantified and measured in single cell experiments. And long back there was a pioneering paper in PNAS where they said that stochasticity randomness plays an important role in cell differentiation. They were the first to propose that stochasticity has a role in cell differentiation. And then the other papers came out with titles like Do Stem Cells Play Dice? So experimental observations. Now people can carry out single cell experiments, they can measure the histograms, and they found that non-genetic heterogeneity are a feature of both embryonic and adult stem cell populations. The same genetic population, the same environment, the same initial state, but in the course of time, there is a spread in the protein levels. And this is the paper, experimental paper, which is pioneering, Chan et al. Nature 2008. They found that there is a nearly 1,000-fold range in the levels of stem cell marker protein. The name of the protein is Ca1 in a clonal population of mouse hematopoietic progenitor cells. Hematopoietic cells are blood cells. So differentiation of blood cell into white blood cell and red blood cell. So this is the experimental graph, number of cells, and log fluorescence is log protein concentration. And they showed a 1,000-fold range in the level of the protein Ca1. And stochastic dynamics, so in the case of stochastic dynamics, if you have a snapshot of a clonal population of identical cells, in the deterministic picture, you have 10,000 cells, each cell gives you the same protein level, so you get a single protein level. But here in the state space, instead of a single sharp point, you get a cloud of points, each representing the state of an individual cell. So now you have to define probability PS that the cell is in state S. This is the outcome of randomness, and stochasticity helps in choice of lineage in cell differentiation. I told you that in the mammalian sulfate T, at each branch point, the cell has a choice between two lineages. But then how does the cell choose the lineage? So the answer is given in this diagram. So you can draw a landscape. How? You can draw a potential landscape. U goes as minus log PS. So this is U drawn in the state space. This is the potential. Potential U, you can immediately realize that the minima of the landscape, that is the minima of U correspond to the maxima of PS. So the lower the position of the valley, higher the stability of the state. So this is the undifferentiated, just one second. This is the undifferentiated cell states, and these balls, they represent cell states. Because of fluctuations, they can wiggle around in this valley. This is the undifferentiated state, and by chance, say one cell state is located close to the periphery of the valley, then the slightest noise will make it fall down into this valley. This is one of the differentiated cells. This is blood cell differentiation into myeloid cells. These are the white blood cells, and this is the erythroid cells. This is the red blood cells. Differentiation of blood cells into red blood and white blood cells. So blood cell differentiation, erythroid and myeloid. I hope that through this cartoon, I have been able to explain what is the role of noise. The noise helps in the choice of a lineage. This is computation, but recently people have carried out microarray experiments. This is a famous paper, and there they draw trajectories in state space. They show that they are tending to a particular point. They show that due to noise, there may be a transition. Fantastic experiments are being carried out to show the effect of role of noise. And noise need not be a nuisance. That is the lesson you learn from the studies in biology, that noise often helps the living cell in carrying out particular tasks. One of these is to make a choice, to decide, so to say. And so, so this is a landscape, see, and the valleys correspond to the distinct cell types. So Stuart Kaufman, in pioneering papers, he said that different attractors of gene expression dynamics constitute different cell types. So in the landscape, the valleys correspond to distinct cell types, and the tops of the hills are the stem cells. So here lots of problems are lurking for physicists and mathematicians. What is the optimal path from an undifferentiated cell state to another, a differentiated cell state to another differentiated cell state, maybe from the kidney cell state to liver cell state. If you look at this diagram, it gives you the idea that previously people thought that cell differentiation is irreversible. From the embryonic stem cell state, you differentiate into lineages and further differentiate into further lineages. And they thought you cannot reverse the process. But at that time, stem cell research was considered to be unethical. It was banned in many countries because you have to pick up the stem cells from embryos. That was considered to be unethical. But then the Japanese scientist, biologist in 2009, just look at this. They showed what is the protocol to be followed. You have to follow a protocol so that the cell leaves the valley and goes to the top of the hill. And they could do it by certain protocols. So that once, for example, they took adult skin cell and converted it into stem cells. So now there is no ethical issue. You can now borrow that stem cell and inject it into your, only 5 minutes. Okay. And this Japanese scientist got the Nobel Prize. This is called reprogramming of differentiated cells to induce pluripotent cells. So there are many interesting possibilities, and everywhere I think physicists and mathematicians, they are contributing in a meaningful way. Pratap, I'll just hurry and then maybe. The stochastic dynamics, instead of a single state, one obtains a probability distribution. So we solved the appropriate Langevin equations, add noise terms to the deterministic equations, and we got this probability distribution for the undifferentiated cell state. This is called pluripotent state, that the state has many possibilities, different possibilities. And this is a macro state. And here I'll just draw some analogies with statistical mechanics. There is a beautiful paper, Statistical Mechanics of Pluripotency. So we know that ideal gas in a closed container, the microstate at time t is defined by instantaneous positions and momenta of gas molecules. And the numerous different interchangeable microstates realize the same macrostate. Macrostate described in terms of average properties like pressure. Similarly, draw analogies. Pluripotent, undifferentiated state, a macrostate. Cells are analogues of gas molecules. Protein concentrations analogues of position and momenta. And microstate at time t is defined by the set of instantaneous protein concentrations in the individual cells. And you must be familiar with the maximum entropy principle, that you have this form for the entropy, SPI, PI log PI. P is the probability the system is in the state I. So James said that the state which you get can be selected through by using the maximum entropy principle, maximize PI, keeping the constants of the system in mind. And this is how we derive Boltzmann distribution in statistical mechanics. So remove a constraint, entropy increases. For example, you have a gas in a cylinder confined by a piston, undifferentiated cell population, entropy is large. Here, undifferentiated cell population, differentiated cell population, stronger regulatory constraints, x1 has to be much larger than x2, or x2 has to be much larger than x1. So decrease in entropy, uncertainty. So in another paper, entropy, ergodicity, and stem cell multipotency, actually I don't have time to explain everything. In our paper, what we showed mathematically was that whatever experimental observations have been made so far, they are an outcome of, they are nothing but signatures of criticality. The criticality is associated with the bifurcation point. And these people took up our suggestion. They looked at the actual experimental data, analyzed the data, and what they showed was the following. Here, just look at this. The green circle is the maximum entropy distribution. And the experimental distribution is very close to the, this is the magenta cross is the experimental distribution, and the green circle is the maximum entropy distribution found from maximum entropy principle. They are very close to each other, and they are also located very close to a critical boundary separating bistability from monostability. And they cited our paper, they saying that we find evidence of their conjecture in this paper. So now I'll just, since I don't have much time, I'm just keeping the mathematical part, which was elementary and interesting, but just I'll show the final figures. So in the experiment, what they find is the following. You have a parental distribution in the undifferentiated cell condition. So what they did was they deliberately, they divided the parental population into 3 subpopulations and let them separately. So in the course of time, again the parental distribution was regained. But it was very, very slow kinetics. The regaining was over a period of 2 weeks. So the puzzle was first, why this broad heterogeneity? Second, why the slow kinetics? And as the cell was going towards the differentiation point, the variance started increasing. So they could not explain all this. So in our paper, we have explained all these features. I'll show you the final graphs. We found out that there are 2 modes in the dynamics, slow dynamics and fast dynamics. So this is the state space, x1 and x2 are the protein concentrations. This is the direction of dynamics, the fast mode dynamics, and this is the direction of dynamics, slow mode dynamics. And we showed that ultimately all phase space trajectories, they are becoming tangential to the direction of the slow mode. That is ultimate, but this is very slow kinetics. And you remember that in thermodynamic phase transitions, we had this critical slowing down. The close to the critical point, if you perturb the system away from the equilibrium state, the system requires some time to come back to the critical point. At that time slowly increases as you go towards the thermodynamic critical point. It diverges. This is called critical slowing down. The same thing you observe close to a bifurcation point. As you go towards the bifurcation point, the system is in a stable steady state. You perturb the system, take it away from the stable steady state, measure the time needed to regain the stable steady state. This time goes on increasing and it diverges close to the bifurcation point. Very two recent experiments have been published in Nature showing this for biological systems. So this is critical slowing down, and then we did extensive numerical simulation and showed that the direction, what we showed was the following: near criticality, the direction of slow relaxation is also the direction of large fluctuations, the distribution of which is non-Gaussian. So this is the slow direction, and see here the spread is much, much larger. These are the protein levels, the states, and this is the fast direction. Here the spread is very small. So now we could explain the experimental observations. This is the experimental data. SCAR1 levels exhibit the features of criticality, slow kinetics, large variance, and non-Gaussianity. We could show all this. Just 2 minutes, GP. Just 2 minutes. And there are critical slowing down is one signature. Another signature is rising variance as you go towards the bifurcation point. And another signature is this lag1 autocorrelation function. This also increases as you go towards the bifurcation point. I can give you physical insight why this is so, but for lack of time, just accept my words. This is the lag1 correlation function. It is a measure of how much the state at time t plus 1 resembles the state at time. And so here is a cartoon. This is from a paper in Science, that originally you have bistability, but as you are going towards the bifurcation point, one of the states is losing stability. Here the stability is lost and you are left with monostability. And this is another cartoon, that away from the bifurcation point, you do not have slow kinetics, but close to the bifurcation point, because the slope is low, rates of change also become low, and it takes a longer and longer time to attain the stable steady state. And because rates of change become slow, close to the bifurcation point, the fluctuation accumulate. They do not have the chance to decay, so the variance increases. Because the rates of change is slow, the future resembles the past more and more, and autocorrelation is greater. So all these things we could show and in our calculations. And the interesting thing is that now papers are coming out in the last 1 to 2 years supporting our conjecture. This was a bold conjecture, and so these are the references. Sulfate decision as high dimensional critical state transition. These are all experimental papers. Not that another theory group is just giving support. These are experimental biologists. Similarly, single cell based analysis highlights a surge in cell to cell molecular variability preceding irreversible commitment to a differentiation process. And they conclude our results fully supported a dynamical view where differentiation can be seen as a critical phase transition driven by stochasticity. And similarly, another paper where they showed that the variance increases as you go towards the signatures of criticality in biological systems beginning to be identified. These are pioneering papers. I will not go into them. Another very recent paper, that criticality in which physicists may be interested, the criticality in biochemical feedback, non-equilibrium system of biochemical feedback near a bifurcation point exhibits critical properties characteristic of equilibrium systems belonging to Ising-Minfield universality class. And quantitative theoretical predictions verified in single experiments on T-cell signaling. We have done some more work showing self-organized criticality. Again, this can be verified in experiments, but for lack of time, I'll skip all this and we'll just show you some references. So the references themselves will give you a flavor for the interdisciplinary character of this area of work. This is scaling for, okay, I won't have time. So these are the two major papers, and then criticality in cell differentiation, statistical mechanics of pluripotency towards the statistical mechanics of sulfate decisions, and stem cell differentiation is a many-body problem. People are using quantum mechanical operator formalism to carry out many of the mathematical steps. And this is a very good paper, Entropy, Ergodicity and Stem Cell Multipotency. Thanks.
Thank you. So, as you can see, this is a cutting edge area in condensed matter and bioscience. And let's see if there are any questions or comments. Yes.
So, as expected, it was a very stimulating talk. So I was wondering that the slow and fast dynamics near the critical point.
Speak a little more loudly.
Yeah, the slow and fast dynamics near the critical point, does that originate from the timescale separation of your transcriptional interaction and protein-protein interaction?
No. It's a two-body system, two proteins, and so if you carry out linear stability analysis, the Jacobian matrix is 2 by 2. And it has 2 eigenvalues, 2 eigenvectors. And the general solution is a linear combination of these two solutions, and they involve the factors e to the power lambda 1t and plus e to the power lambda 2t. And lambda 1 and lambda 2 should have real negative values, because ultimately the state has to come back to the steady state if it is stable. So, so slow mode corresponds to the value of lambda which is closer to 0. So that takes a longer time for the cell to decay to the steady state.
And also
there is no further.
Okay. And also in your Najwa equation, the noise statistics, did you allow for any spatial and temporal correlation?
Yes, here also we measured correlations between the two variables x1 and x2, because they replace each other. We found perfect anti-correlation as you approach the bifurcation point.
In the noise statistics, I'm saying, like if you so the distribution, it seems like non-Gaussianity, right? So is there any like temporal and spatial correlation in your noise process itself?
Non-Gaussianity appears because originally you had a double well potential, but one of the wells is losing stability, becoming shallower and shallower. So asymmetry is developing in the system, and that gives rise to this non-Gaussian distribution. Maybe we can discuss these things.
You focused on the cell differentiation at a bifurcation point. But at the beginning you also showed this fantastic landscape through which all these cells, let's say, are created.
Right.
Who gives that landscape? How can one sort of work out a simpler model of such a landscape? Or because you don't have a background here giving you the landscape.
Right.
It's all only the stem cell which interact with each other and somehow produce the landscape as they get along.
Right.
So how does one address this kind of problem?
That's the key question. The thing is, first you have to identify biological systems are complex systems. So if you consider everything, you may get bogged down in data. Clarity will be lacking. You cannot answer general issues. So one has to be very inventive and extract the most dominant features. So here we used a very simple motif, the 2-gene motif. And there you can easily construct the potential landscape, because this is nothing but minus log PS. I carry out some calculation, either I solve the master equation or I carry out some numerical simulation or solve the Langevin equations, and I have a knowledge of P, and so minus log P is your U. So you can construct that, but constructing that landscape which I showed you, this is non-trivial, but right now I told you that fantastic experiments are being carried out. People are actually carrying out experiments. They are using this terminology of state space, trajectory, probability distribution, and for simple cases they are coming up with these landscapes. And similarly, gene expression, protein concentration can be anything. But there, another set of people, they are using a simple description called Boolean gene expression. That gene expression can be either, protein level can be either 1 or 0. That if the gene is active, it is 1. Otherwise it is 0. So the state space becomes simpler. You can handle things in a much better way. So there lies the challenge, whether you can meaningfully construct a landscape, then connect to actual experiments. Can you go to experimental biologists and tell them, do this, do this, do this? You should be able to convert a kidney cell into a, say, liver cell. If we can do that, I mean, fantastic possibilities.
Thank you. I think I want to. Okay, that's quick. Very
The
good.
bifurcation you talked about, can it happen simultaneously at different places because there are different branches? Huh.
Now the branch you get as you change the bifurcation parameter, to fix the parameter, make the experimental measurement, change the parameter, make the experimental measurement in the steady state. That is how you are getting the branch. But what you are saying is a good question, that you are saying that bring in space. So that will complicate matters. Here we are assuming that we have a sort of homogeneous mixture. We are just looking at the time
I am
evolution.
sorry, I have to come to such an interesting thing. I myself had some questions, but I'll ask it separately because I have to look at my watch. So then let's thank once more Professor Bose, and now we move over to the third talk of this session, which will be delivered by Professor Prabhat Mandal. As most of you know, Professor Mandal has been involved with the experimental condensed matter physics department of SINP, and lots and lots of innovative things on electronic and magnetic properties, and I think more recently delved into the topological matters and the Dirac materials. So today's talk is, you can see.
Okay. Thank you for. I first of all thank the organizer for giving me the opportunity to present our work in this forum. And this is also after a long time in Kolkata, such a big kind of activity. So this is really nice to be together and listen different kind of talks in different areas. This is one of the new areas, and we started. We are working last 2 years only, and many of the things we do not understand, and theory also you know very new, and so I am not going to present any theoretical equation or idea. I only present experiment, and wherever it is required some expression for explaining our result. But I think the result itself important, and you can differentiate with existing systems which so far we deal with. And by the way, most of the systems, almost all the systems are very old, and they studied during 60s. And many physical properties which I am going to present, or people, many of them are old, but physics is new. This is the thing. Not many of the measurements were done during 60s and 70s, but people did not know what is the physics, rich physics behind this. Okay, with this, so the title of my talk is Titanic Magnetoresistance and Signature of Non-Degenerate Dirac Nodes in Zirconium Silicon Sulfur. Let us see how far I can go. Okay. An interesting thing is that this field of research involves different branches in science. For example, condensed matter physics, material science. Why material science? Because these are the materials earlier known as thermoelectric materials. Because of high conductivity and large value of thermoelectric power, they are known as thermoelectric materials. And this is very, that's why it is very old. People for a long time working in this field for practical and technological application. But several experimental tools that is new, that were not applied before. And many other branches, particle physics, most of the theoretical idea came from particle physics. In fact, a few days before, one of my colleague in particle physics, he says that, well, many of the particle physicists now, they are changing towards the condensed matter physics. So this is one, maybe you can see one of the speakers sitting here, she is also from other branches of physics, but recently working in this field. Okay. Just maybe